have a 1 in the bit 5 position for lowercase letters, and a 0 in this position for capitals. So the bit positions are numbered from right to the left, starting with 0. From right to the left, starting with 0. What will be the result if you all ask letter with the 8-bit mask? Use this number. Use this number. In the 5th position for lowercase letters, and a 0 in this position for capital. Then the resulting letter will be lowercase, but the 5, 1, 2, 3, 5 is 0. 0, right? The 5th position, 1, 2, 3, 4, 5. The 5th position is 0. So 0 can be set to 1. It's wrong. It's wrong. This must be this. Must this number. 1, 2, 3, 1, 2, 3, 4, 5. Right? The 5th position is 1. The 5th position is 1. Then if the letter is a capital letter, then we use on all operations. You use on all operations like this. Then the capital letter can be converted to all lowercase letter. Because this position converted to 1 for the capital letter. Because 1 or A equals 1. Understand? BCC asked to can find the up to number of one letter. If you know one letter is up to two codes, they can understand this easily. If we want to, for example, if we use to represent, if we suppose that this this binary number is on ASCII2 code. ASCII2 code. It represents capital letter B. It represents capital letter B. Then we all these ASCII2 letters with the mask. With the mask 0 0 0 1 0 0 0 0 4. All these letters. Then 1 or 0 equals 1. 1 or 0 equals 1. 0 0 0 or 1 equals 1. 0 0 0. Right? Then this ASCII2 code. The ASCII2 code represents the locale of B. Locale of B. So we can use this OR operation to convert all capital letters to all lowercase letters, or convert all lowercase letters to all capital letters. This is the one kind of function for OR gate. But the exact ASCII2 name for B is not this number. We should find the table, the ASCII2 table. The fourth gate, an AND gate. An AND gate. The AND gate produces a low output when all inputs are high. Otherwise, the output is high. In fact, it is the combination of AND gate and inverter, right? This gate is the combination of AND gate and the inverter, because the two variables, first AND and they invert, So the truth table is like this: A and B equals 0. 0 then invert 1. So the result is 1. 0 and 1 equals 0. 0 inverter and 1. 1 and 0 0. 0 invert to 1. 1 and 1 equals 1. 1 invert to 0. So the truth table result is 1 1 1 0.
This is the opposite of AND.
Yes. So the AND operation is solving the dot between the variables, and on our bar converting them. Thus, the AND operation is written as A and B over bar, or A equals AB over bar. AB over bar. Another kind of expression is X equals A and B, like this. It is also represent an A, or like this, an A and an N. The example waveform is also like this. Only when both the variable A and B are high, then the value of X are low. So the example waveforms are like this. The AND gate is referred to as a universal gate. Universal gate because all other basic gates can be constructed from an AND gate or universal gate. Other basic gates can be constructed from an AND gate. For example, how will you contact on two input AND gate to form a basic inverter?
Two input and
Very easy, very easy. Two input.
NAND gate for a basic inverter.
Yes, it is very easy. For the inverter, it has one input and one output. For the AND gate, there are two inputs and one output. So we must combine the two inputs to one input. How to combine the two inputs to one? Yeah, it's very easy. We can input A and A to the two inputs. We can input the same value to the two inputs. Then it can be formed to a basic inverter. The NOR gate produces a low output if an input is high. If all inputs are high, the output is low. So
0, 0 equal 1.
So the result is 0, 1, 0.
Everything is 0.
Yes. The NOR operation is done with a plus sign between the variable and an overbar, converting them. The NOR operation is written as A or B overbar. So it also can be represented X equals A or B, okay, like this. It is also represented NOR gate. The example waveform of NOR gate are also like this. If any value of A and B are high, then the output is low. So the value of the yellow area are low. When is the LED is on for the circuit shown? This is on LED. It can emit light. When the value of X is low, because the voltage of this point is 5 volts, and if the volt of this point is 0, then the LED can emit light. So if X equals 0, if you want to make x equals 0. We only need to make A, B, C, or D
Anyone is
high. High. NOR gate. XNOR gate. The seventh gate. The seventh kind of gate. XNOR gate produces a high output only when both inputs are at offside logic level. Offside logic level. If they are offside, and the symbol is like this. So, what is the value of x? 0 or x or 0? 0 x or 0 because they are same. They're same. So the result is 0. Because they are offside, so the result is 1. They are offside, so the result is 1. They are same, so the result is 0.
0
Yes. The expression of XNOR gate is like this. Ordinarily, it can also be written with a circle plus sign between the variables. Like this. This sign represents XOR, or circle plus represents XOR. The waveform is also like this. When they are offside, the output is high. The output is high. So the yellow areas are high. If the A and B waveforms are both inverted for the above waveform, how is the output affected? There is no change in the output. There is no change in the output. Both inverted for the above waveform. XNOR gate. The XNOR gate produces a high output only when both inputs are at the same logic level. So the result, if A and B are the same, then the output is 1. They're same, so the output is 1. So the output of X is 1, 0, 0, 1. The XNOR operation, so the X equals A over bar and B over bar plus A and B. Alternately, the XNOR operation can be shown with a circle dot between the variables. This sign, second dot represents XNOR, and the circle plus represents XOR, right? XOR. Circle plus represents XOR. Circle dot represents XNOR. The waveform is also can be found, because if both are the same, if both values are the same, the output is high. The output is high. So the waveform of X is like this. This makes it useful for comparison function. If we want to compare two numbers, if they are same, the same, then the output is 1. If they are opposite, then the output is 0. Output is 0. For example, if the A waveform is inverted, but B remains the same, how is the output affected? If the waveform of A is inverted, 0 become to 1, 1 becomes to 0. What is the waveform of X? Also 1 becomes to 0, 0 becomes to 1.
Yes.
So the output will be inverted. Okay. We have learned many logical gates, and the logical gate can be integrated into one chip. They are called fixed function logical gates. For example, for this chip, there are 4 AND gate, AND gate, 4 AND gates in one chip. 0, 2. There are 4 XNOR gate, in one chip. GND is the reference voltage 0 volts. And VCC equals 5 volts. 5 volts VCC. Okay, this therefore there are 6 inverters in one chip. 6 inverters, and there are 4 AND gates in one chip. 3 NAND gates, but the inputs of each NAND are 3. There are 3 inputs. There are 2 inputs, and also there are 3 inputs. AND gate. There are 4 inputs. NAND gate. There are 4 inputs. AND gates. 3 inputs. No gates.
8 inputs.
8 inputs. 1, 2, 3, 4, 5, 6, 7, 8. 8 inputs. NAND gates. OR gate. Right? OR gate. 2 inputs. XNOR gate. 2 inputs. Okay. So we have learned chapter 3. The key terms are inverter or logic circuit that inverts or complements its inputs. Truth table, a table showing the inputs and corresponding outputs of a logic circuit. Timing diagram, or diagram of waveform showing the drop time relationship of all the waveforms. Boolean algebra. the mathematics of logical circuits. AND gate, a logical gate that produces a high output only when all of its inputs are high. And OR gate, a logical gate that produces a high output when one or more inputs are high. NAND gate, a logical gate that produces a low output only when all of its inputs are high. NOR gate, a logical gate that produces a low output when one or more inputs are high. XNOR gate or XNOR gate, a logical gate that produces a high output only when its two inputs are at offside level. XNOR gate or XNOR gate, a logical gate that produces a low output only when its two inputs are at offside level. Question. The truth table of a two input AND gate is, please see the PPT. Hi, see the PPT. What is the answer? AND gate. What is the truth table?
AND gate.
AND gate. A, B, C, or D? AND gate. It's very easy. C. Yes. Only all the inputs are high, then the output is high. Question 2. The truth table of the NOR gate is NOR gate. So only when all the inputs are zero. B. Yes. Only when all the inputs are zero, then the output is high. Yeah. So the answer is B. Question 3. The truth table for two input XNOR gate. XNOR gate. Yes. Only when
Opposite value is high. This
at
output is
offside.
high.
At offside.
And same is zero.
So the answer is A. Question 4. The symbol is follow
XNOR
A, B, C, or D.
XNOR.
Okay, I think the answer is A.
OR gate.
69. Okay.
OR gate.
Yes. Right? Okay.
Yes.
Okay. 69. Okay. And the symbol.
XNOR gate.
XNOR gate. NOR gate.
C.
Okay. B, C. No.
XNOR gate, sir.
XNOR.
XNOR, because
And the answer.
option is not here.
Oh. Right. XNOR gate.
Yes.
XNOR gate. Master. Add on X. The logic gate that produces a high output only when all of its inputs are high.
OR gate. All inputs are no. AND gate. B.
Yes, B.
All inputs are high, output is
AND gate. Yes. 7. Operator A,
XOR gate.
X or B. Yes.
XOR gate.
X no.
OR gate.
X no B.
That's
Right? X or X no.
C.
C, right? Yeah, C.
This is the XNOR gate.
Yeah, yeah.
This is
Yeah.
plus, so this is
Yeah,
minus.
C. Our two input gate produces the output shown. This is
This high.
when all the values are high,
This is
right?
low.
When all the values are high, the output is low. Output is low. So. NAND gate.
D.
NAND gate. Yeah, D. NAND gate. Or two input gate produces a high output only when the inputs agree. Agree. What is the meaning of agree? When input produce a high output only when the inputs, the type of gate is agree is the same. The same. So the answer is D.
XNOR gate.
D. Agree means the same.
Same.
So the answer is D. 10 question. The required logical for PLC known we have learned. We have not learned the programmable logic.
Yeah.
Programmable, so we don't need to know the answer. So we have learned chapter. We have learned chapter 3. Okay.